Okay, we're going to start 13.3, and we're just going to do a piece of it. There's quite a bit of material here, but we're just going to focus on the first part, which is on arc length. And so what we first want to do is derive a formula for arc length. And so we do that by doing the following. So suppose we're given r of t, some vector valued function, which is x of t, y of t, and z of t. And let's suppose we're on some finite interval, a to b. And let's just draw some type of curve here. So we're somewhere in three-dimensional space. And our curve is something like this, where we start here at the point, so here's r of a, here's r of b. So what is the idea? The idea overall is to, just like in single variable calculus, to split up this. So first we split up this time interval. So we split time interval into some number of segments, into some number of segments. Oops. Should practice my spelling here. Segments. And what do we get? Well, what we're going to do is we're going to approximate this arc length with a bunch of lines. And I'll just draw an example here of if we had, say, 5 equally, let's just assume that those are equally displaced in time. They don't have to actually be the same length of each of these lines. So we'll call this L1. This would be L2. This would be L3, L4, and L5. So what would those, what would L sub 1 say actually be? L sub 1 would be, well, I have, well, we have this is the distance between r of a and r of a plus some delta t, where in this case, the delta t is b minus a divided by 5. Right, we're splitting it up into 5 segments here. So we've split up overall this time interval into 5 pieces. And for simplicity, let's just call this r of t1, where, and then t0 is a here, t1 is the next point. So essentially L1 is the distance between r of t0, which is a, and r of t1. Well, what is that? This is equal to, we'll call it x1 minus x0 squared plus y1 minus y0 squared plus z1 minus z0 squared. This is a kind of shorthand notation where x sub 1, y sub 1, z sub 1, these are x of t1, y of t1, z of t1, etc. So in general, I'm just going to denote x sub I to be x of ti. And similarly, y sub I is y of t sub I. Z sub I is z sub ti. And so this L1 is this length right here. So let me just... And similarly, you can see in general, so if right now instead of 5 pieces, I just chose 5 as an arbitrary number. But as you know from calculus, as you increase the number of, sorry, let me do that with red. So here's our curve. If you have a lot more little line segments, then you're going to get a much better approximation. Oops, get rid of that last one. And so as n, so let's denote n, if n is equal to the number of sort of divisions of the interval a to b, then as n goes to infinity, the summation of each L sub I. So L sub I here, this is, so L1 would be right here, L2 and so on. And you'd have the last one being L sub n. So this sum, where again L sub I is the length of the ith line segment. If we compute the sum of these, then this is approximately the arc length. And this is the key fact to note. So let's just rewrite what this is. So the arc length then is it's actually equal to then the limit as n goes to infinity of the summation, and L sub I, what is that? That's x sub I minus x sub I minus 1 plus y sub I minus y sub I minus 1 plus z sub I minus z sub I minus 1, and these guys are all squared. And summation then goes from I equals 1 to n. So in shorthand, we can simply write it this way. This is simply the change in x. This is delta x. This guy here is delta y. This guy here is delta z. All right. And, well, I guess just to be kosher here, this is at the ith place, because these are all dependent on where this is located exactly. But now what we can do then, we multiply the top and the bottom by delta t. So let's multiply the top and the bottom of this overall expression, which I've put in red parentheses. Let's multiply the top and the bottom by delta t. Well, what happens then, if you actually see what this is, then this is equal to, and here we get delta xi divided by delta t squared. When you throw this, the denominator delta t, when you put that into the square root, it squares, and hence we get this guy squared. And then plus, similarly, delta yi divided by delta t squared, delta zi delta t squared. And what happens as n goes to infinity, note that as n goes to infinity, delta t goes to 0. And as delta t goes to 0, this delta xi divided by delta t, this goes to x prime of t. Okay? So this is an important fact that hopefully you would have seen at some point. So this is the change. Basically, we're having change in x over change in t, and that's when the change in t gets smaller and smaller. This is exactly basically the definition of the derivative, right? Because this is just r sub, oops, not r, x sub I of ti minus 1 plus delta t minus, sorry, no, we don't need the subscript here, x of ti minus 1 divided by delta t. And this is exactly converging to x prime ti minus 1. Okay, so this converges to, in general though, we can just simply write it as x prime of t. So this overall converges, this converges to the integral of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt, and then we have an integral going from a to b. So this is actually your arc length formula. So our arc length here, I'll just call it a dot l, is equal to, I'll just rewrite the same formula, except I'll write it in a different way. It's the length of r prime of t dt. So this is the shorthand notation for what we just wrote, because this thing right here, which I've labeled in red, this is exactly the length of r prime of t. And so we get this arc length formula. It's a useful formula. It's a generalization of one you probably would have seen in single variable calculus. It's more general than that. So let's just do one or two examples here. So let's say r of t is cosine of t, sine of t, and t. So this is that helix that we talked about at some point. And let's say we're taking 0 up to, say, 3 pi over 4, and we want to find the arc length. Okay. Well, what do? We take r prime of t, which is negative sine, cosine, and 1, and we find its length. In this case, we get sine squared plus cosine squared plus 1, which is simply the square root of 2. And so to find the arc length, and so, well, let me just draw a picture here. This thing will look approximately like, so let's see, I'll have pi halves over here and something like, so in general, the curve keeps going right here. We'll probably be starting somewhere here and looking at just the piece that goes up to, somewhere over here. I'm just approximating right now, but this is what we're looking for visually. So this is equal to the integral from 0 to 3 pi over 4 of the square root of 2 dt. And so this is just the square root of 2, square root of 2 times t, evaluated from 0 to 3 pi over 4. And this is square root of 2 times 3 pi over 4. All right, I'll leave you here with a little exercise. And this is a bit deceptive because the problem is not that straightforward. It is a bit challenging, even though it doesn't look that bad. So let's say r of t is t comma t squared, and this is just essentially a parabola, right? This is your parabola in R2. And let's say you wanted to find the arc length from t equals 0 to t equals 1. And you'll see why I'm saying that it's a little deceptive. The reason why is because the integral, so just set up the integral. Set up the integral. The actual integration is a bit involved. Probably not going to give you that kind of problem to do on an exam, on the final. But it's a good exercise to try, and I will do that in the next video. Okay. Okay, till next time.